I welcome you for this NPTEL course on earthquake resistant design of foundations. And as informed, I myself is Prof. Maheshwari from Department of Earthquake Engineering, IIT Roorkee. In this course, we have 5 modules. First one, introduction, which has been already covered, and the second one, shallow foundations. We are covering right now in shallow foundations. Then once it is finished, we will go for pile foundation, well foundation, and finally soil stress interaction. Today, we are continuing with the shallow foundations, the last part of the shallow foundations. And what you have in this module 2, as we have discussed, these are the components of the shallow foundations. One is the general requirements, where we have discussed that modes of failures, including general shear failure, local shear failure. Then we have also discussed in this case the effect of various parameters. The next one was on bearing capacity and settlement, where we have mostly discussed Tarjagi's theory for bearing capacity and IS code also 6403, which deals with the bearing capacity of soils. And then we do have discussed the effect of various parameters, including the shape of the footing, water tables, and so on. And besides Tarjagi's theory, other theories including Mehrov's, and those also discussed. And later we have also discussed settlement. Then we have talked about combined footings. Combined footings will be required when the shallow foundation, this strip footing or isolated footing is not adequate. In that case, the next choice should be the combined footing, particularly for earthquake or dynamic loads. In case of combined footings, we have rectangular footings, then trapezoidal, and then we also discuss strap footings. So, all these has been already covered. Then finally, the code for raft foundation has been discussed in detail, where we have discussed various theories. Depending on the different conditions, we can either go for elastic method, or we could go that is for ridge foundation, or we could use the flexible foundations. So, all these has been already covered. But what may happen during the earthquakes or dynamic loads, whatever the treatment we have done so far, that is why I have reviewed it again today, that is for bearing capacity and settlement, or for combined footings or raft foundations, that may not be enough. In that case, we do not have any choice, we need to design our footings for dynamic loads. So, today this is the last part of the shallow foundations, which is footings subjected to dynamic loads. And under this topic, we are going to cover these topics. First, let us discuss what are the dynamic loads and methods of analysis. Then we are going to talk about pseudostatic analysis, what type of loads can be considered during earthquake loads, which may represent the earthquake loads. Then we are going to talk in very much detail the eccentric loads on footings, that means is a point load which is not at the center, rather acting at some eccentricity from the center. Then the next one is a new method for design of eccentrically loaded footings. Today we are going to talk about its bearing capacity and settlements. So, in the first lecture of today, we are going to talk about this. Later on in the second lecture, we are going to talk about what are the design procedure for this new method. One design example will also be discussed in detail. And finally, when you have inclined load on a footing, so how to deal with that. So, that is also going to be, we are going to discuss besides the eccentricity of the loading. So, now let us discuss the first one, that is dynamic loads and methods of analysis. When we talk about dynamic loads, you may be aware that foundations are subjected to dynamic loads due to many reasons. One of the reason is earthquake or seismic loading. When we talk about earthquake apply the lateral load, that is the basic difference. When you do not consider the earthquake, vertical load will be always acting, but it is the lateral load which is must during the earthquake to consider. Suppose if we say we are considering the earthquake load and then only we consider the vertical load, so that will be not a fair thing. So, the lateral load or horizontal load, that is predominantly important for earthquake loads. Then when we talk about blasting, The load may be even though vertical, but it may be varying with the time. So, that may be again dynamic loading, then there could be operation of machine or there could be wind loading also. So, these may be the reasons for dynamic loads. And methods of analysis, when we talk, then you have pseudostatic analysis and dynamic analysis. So, let us first discuss pseudostatic analysis before we go for dynamic analysis. When we talk about pseudostatic analysis, you may be aware that this is the type of analysis where earthquake load are represented by a that is you have, let us say, W in this equation. W is the vertical load, and then when you have W vertical load multiply by some factor, which will give you this the horizontal load. So, what you have here, then similarly, so if I multiply with W with KH, then you get the horizontal force equal to FH. Same way, if I multiply W with KV, then I got FV. So, these are the horizontal force and vertical force due to the seismic load, which is considered as a static load, but one is acting in the lateral direction, another is vertical direction, where KH and KV are called horizontal and vertical seismic coefficients. KH and KV are the dimensionless parameters. So, KH can be found AH or W, while KV can be found AV or W, AV or G. So, you could see naturally the how this is the most commonly used for the designing of foundations which are subjected to earthquake loads, and here most important issue for pseudostatic analysis is selection of value of KH and KV. So, and naturally normally what is done, KV is assumed half or 2/3 of KH. So, what is the proposition, KV equal to half to 2/3 of KH. So, once we fix the value of KH, then we can find the value of KV. However, KH itself will depends on what we call the intensity of the earthquake or magnitude of earthquake, severity of earthquake, and naturally if we do not have any data or time history, then KH can be linked with what we call the seismic zone. So, KH can be simply linked with seismic zone, and you may be aware that our country has been divided in 4 seismic zones, zone 2nd, 3rd, 4th, 5th. There are many theory, many hypotheses. However, the value of KH is typically taken as on the conservative side half to 2/3 of zone factor. So, KH can be simply half to 2/3 of zone factor, 2 times of Z, where Z value, for example, if I go for zone 5, what you will get for zone 5? Zone 5 KH can be approximated half to 2/3 of 0.36. That means you get 0.18 to 0.24, and if I get the average values of this, what you will get about approximately 0.21. So, this is an approximate value for this KH, and that is the and this is quite severe. More than that, considering this KH more than that, this will be very conservative. So, KH normally if we want to have the higher side, then KH is typically taken as 0.2. On the lower side in the medium zone, KH is 0.1. So, my recommendation for KH is to take 0.05 to 0.20 according to seismic zone, and then once you fix the KH value, then you can decide the value of KV. Our code IS 1893 suggests that the KV should be 2/3 of KH. So, this latest code 2016 as well as 2002 says that vertical acceleration should be 2/3 of the horizontal acceleration, though earlier code it was half. So, you whatever value you can have for decide for KH, you can have KV equal to 2/3 of KH. Continue with that. So, once this is once we decide this load, then the seismic load in pseudostatic case, then they are assumed to act as a static load. So, that means what will happen when you consider in the pseudostatic analysis, in addition to vertical load, you consider some more vertical load due to the earthquake force, which is equal to Fv as given here, and that Fv may be either acting downward or as well as upward. Both conditions need to be considered, while the value of this Fh will be considered, and that condition in the direction in which Fh is decreasing the factor of safety, that should be considered for the foundation design. So, after this pseudostatic analysis, next one is let us consider exclusive earthquake loads on footings. When we talk about earthquake loads, there could be vertical alternating load where failure follow a static pattern. There could be horizontal alternating load, and horizontal load may what it may do, it can slide the foundation and the sliding may occur, but there could be moment also due to one or more axis, and it will generate slip surface on each side of the foundation. So, let us discuss these type of loads in detail. So, what you have in this slide, this slide is conveying effect of horizontal load and moment, and these horizontal load and moments are due to seismic load or what we say earthquake loads. What do you have here? Three cases, one of the three cases may arise depending on whether the effect of moment are predominant as compared to with the horizontal thrust, or reverse is the case, or there may be the case that effect of both moment as well as horizontal thrust is predominant, then in that case we need to consider the both of them. Let us consider the first case where due to earthquake load, not only you have vertical load, but you have some moment also acting on the top of foundation, which is maybe due to structure load or superstructure, whatever you have. So, that means foundation is not only subjected to vertical load, it is also subjected to what we call the moments, and now you need to design your foundation both vertical load as well as moment. So, if suppose if you do not have the moment, then in this case you could assume that your vertical load is concentric, Q is acting at the center. However, when the moment is there, then it can be considered that you have a vertical load which is not acting at the center, but it is acting at some distance from the center, and that is called eccentricity E, which you could see in this case. The value of eccentricity E can be simply computed using this the magnitudes of given of magnitude of moment as well divided by the Q, where m is the moment and Q is the. So, this case can be simply treated, this can be compared, this case may be simply compared where you have this footing and at the center you have a load Q acting, and then you have if I put this load here and then down here, so this will create a moment. So, you have Q acting and then another moment. So, this load can be treated as vertical load and a moment both acting at the center. This can be replaced by simply a vertical load which is acting at eccentricity E as given in this case. So, moment can be dealt in this way. See that vertical load will be always there. You cannot design or you should not do any analysis where you are considering only moment or horizontal load only. Vertical load will be always there on the footings, and we need to consider that one, whether moment is acting or not acting. So, as a result, now this is the first case where moment is replaced by eccentricity, and we need to consider only a vertical load acting at some eccentricity. Then the second scenario where you have the value of Q as could be seen in this figure, what you could see in this figure, you have a value of Q which is acting, an inclined load is acting, and this inclined load is acting at the center, that is. So, what we can have, there may be two components of this load, one is what we call the vertical component QV and another component QH. So, this will be equivalent to two components. So, that means this condition will be able to deal with a situation where in addition to vertical load a horizontal thrust is also acting. So, this is the second case when horizontal thrust is acting. Now, there could be a scenario where both moment as well as horizontal thrust is acting at the center. That means, in addition to vertical load at the center, you have horizontal thrust as well as some moment. Now, what you have? This can be simply replaced by an inclined load Q, which is not at the center, but acting at some eccentricity E. So, that can be dealt with that. So, all these three cases. So, we will discuss in very much detail all these three cases. So, let us talk the first one, and first one we will talk in very much detail, second and third will be dealt after the once we get some experience from the first one, how to deal with the first one. For dealing the first case where a vertical load is acting with some eccentricity, and we already discussed that this is basically representing your moment. You are replacing the moment with eccentricity, and eccentricity can be worked out with the given value of moment, and Q is the center. Here you need to understand that in given problem you have a Q vertical load acting at the center as well as moment M acting at the center, which is equivalent to an vertical load acting an eccentricity E. So, you could see that in this figure shows the footing under the action of load Q acting with eccentricity E. Now, if you consider the B is the width of the footing, which is normally B, capital B is used for that, and we have used. If your eccentricity E have a value less than B by 6, then the footing is in compression throughout. That means, here you will have, if the value of E is less than B by 6, then on one end, on the end where your Q is acting that side, you will get the what is called Qmax, right. On another end, opposite end, you will get Q minimum. If I put E equal to B by 6, then Q minimum will become 0 and Q maximum will be maximum value of that, and your footing will be continuously throughout in compression. However, if E value get exceed B by 6, then some part of the footing will undergo tension, though we will not allow that, but if your eccentricity is exceeding, then you need to forget that part of the footing, that because tension like that will not help you. So, what happens? So, there will be loss of contact with the soil for 3 times of the difference of E minus B by 6 portion of the width. So, this much E minus, so as you increase the, if E is less than B by 6 or E equal to B by 6, this will be 0, but if the value of E exceed B by 6, then the difference of E minus B by 6 multiplied by a factor of 3 will give you that width where there is a loss of contact between soil and footing, and basically we will need to neglect that part for designing a foundation. So, what is done with that? So, now when we continue with this, so let us consider both the cases. When the value of E is less than B by 6, the maximum value of Qmax which we have just now discussed, can be given by this relation Q by A 1 plus 6 E by B, okay, that is equation number 1A. However, if E is exceeding B by 6, then Qmax will be given by the second equation 1B, where Q by A 4B 3 divided by 3B minus 6 is there. If a case where E equal to B by 6, then either of these two equations can be used, and if I put in both the equations, in any of these equations E equal to B by 6, you know that you get the value of Q max equal to simply 2 times of Q by A. So, you get, and Q minimum in this case will be 0. So, for E equal to B by 6, you can use either of these equations, that is fine. Now, the second scenario, and we already discussed Q minimum will be 0 if you have E equal to B by 6. However, even if E is greater than B by 6, less than B by 6, still your Q minimum may be 0, and that distance will be like, you know, that you can extend this footing, and then if I continue with this, so what will happen if I continue this? So, this will be 0 at some point. So, this will be 0. okay. And this distance of this point from this edge can be find out. What is this distance? This distance is given here, and this is distance of 3 times of b by 2 minus e. That means, what you have here, if you see in this figure, this will be b by 2 and this will be simply, this distance will be b by 2 minus e, right. So, 3 times of this b by 2 minus e from this edge, not from this edge, will be the point where the q minimum will be 0. Okay. So, this is and the concept of effective width b dash or b prime was introduced by Maheshwari in 1953. So, the first Maheshwari has given some very simple philosophy to how to account for the effect of eccentricity in the foundation design, and Maheshwari have simply said that assume that your width of footing is reduced by a factor of 2 times reduced by 2 times of eccentricity. So, if your original width is b, minus 2 times e will give you the effective width of foundation, and this effective or this reduced width of foundation or footing should be used in the design. So, simply what is the meaning of it? That means, as you increase the value of eccentricity, you are going to decrease the effective width of foundation. As a result, your bearing capacity is going to, or your load carrying capacity basically of the footing is going to decrease. Then however, this method is though very simple, but this suffers from the fact that only ultimate bearing capacity is analyzed, but we have not talked anything about settlement. So, later on a new method has been proposed for designing eccentrically loaded footings, and this new method we are going to discuss in this lecture in very much detail, and this is the something which is should be used for the design and analysis of the footings which are subjected to eccentricity. And this new method was proposed by Prakash and Saran in 1977, 71 and 73, and this has been available in the books written by Samsher Prakash as well as Professor Swami Saran. And let us discuss that method which they have proposed, and this method has been proposed by them, not like a new method. An analytical solution of determining the ultimate bearing capacity of strip footing under the eccentric vertical load has been developed, assuming a one sided failure. So, what has been done here, our objective is to get the value of Qu, that is ultimate bearing capacity. However, that footing is subjected to eccentric vertical load. So, that is the condition that eccentricity is there, and how to account. So, what they have proposed, and this their proposed method is based on what we called that test they have conducted in the labs and the field. The results of bearing capacity computation have been expressed in the form of having capacity factor NC, NQ and N gamma, which not only depends on angle of internal friction phi, but they also depend on the value of eccentricity E. And this eccentricity E is expressed in dimensionless form by a ratio what is called E by B. So, basically if I say summary, then what these researchers have proposed, that NC, NQ and N gamma are functions of phi, which is the normal case, but they are also function of E by B. So, in addition to function of phi, they are also function of E by B. So, let us have here. So, what you have, the loss of contact of the footing width with increase in eccentricity, this was accounted for while evaluating the bearing capacity factors, and as for the ultimate bearing capacity equation is concerned, if we neglect the shape factor, depth factor or inclination factor or effect of water table, which was the case in the original Tarjagi's theory, then in that case ultimate bearing capacity is still given by the same relation Q mu equal to C n C plus gamma df n q plus 0.5 gamma b n gamma. And as you know, this equation is same as Tarjagi's theory. So, we have already discussed this equation in very much detail, there is nothing new in this. What is new in this method? N c, n q, n gamma, they need to be have the effect of eccentricity, and we will discuss on these factors and then check the bearing capacity, then later we are going to talk about settlement as well as tilt also. But let us talk first complete about bearing capacity. So, this n c, n q and n gamma, how they are affected by eccentricity are shown in these charts. So, this chart which is taken from Prakash and Saran in 1971, their paper, and their papers figure, this figure represent the effect of E by B on the factor n gamma. So, what you could see, on x axis you have weight factor n gamma, and on y axis the value of phi, which is varying from 0 to 40 degree. Okay. So, for different values of phi, then E by B equal to 0 here. This curve is for, this is for E by B 0, then E by B 0.1, 0.2, 0.3, 0.4. So, there are 5 curves. When you say E by B equal to 0, that means there is no effect of eccentricity, there is no eccentricity basically. So, let us first see the E by B equal to 0. Naturally, when you increase the value of phi from 0 to 40 degree, then the value of this factor n gamma is going to increase. However, for the same value of E, for the same value of phi, let us say for 30 degree, if I draw it for 30 degree, what you could see, for when E by B increases, your this value is decreasing. So, if you could see, this is the value for E by B equal to 0, then this value, and like this. So, these values are basically, you know, that when the E by B increase, this is decreasing for the same value of phi. Here is this table which shows you the data for phi equal to 40 degree. When phi equal to 40 degree, when you do not consider the eccentricity, n gamma is 115. When you consider the an eccentricity ratio 0.1, this dropped to 71. The next one value is 41, then 18, and finally, when you consider E by B equal to 0.4, then this reduced to 4.62. That means how much? From 115 to value come down very much. So, that means there is a very significant effect of eccentricity, and for this effect what you need to consider, that E by B, but as we discussed that we should have try to keep the value of E by B as far possible less than 1 by 6. That means, E by B as far as possible should be less than 0.16, and that means we may not to expect to increase the value of E by B more than 0.2. So, in that case it will reduce from 115 to 41, that means the value of this factor have reduced to 1/3, almost 1/3, less than 1/3. So, this was the scenario for the factor n gamma. Similar chart has been given by these authors for NC and NQ. So, you could see that this is the for NQ, and again the charts are from 0 to angle of internal friction 0 to 40 degree. There are 5 values for E by B as before, and then the table is also given, and here also you could see the reduction is from 81 to 15, but it is reduction is not so large as was the case for the factor n gamma. And here also the chart, the difference is not so much, but if I see the earlier chart, then the difference between these, there was large difference in the values due to E by B. Then the last one, NC. On the factor NC, if you see the effect of eccentricity on the factor NC, then also you can observe that the E by B equal to 40 degree, it was 94 degree, 94.83 NC, but it have reduced to 18. So, there is a clear effect of the eccentricity. So, in nutshell, after discussing all these 3 charts, what we conclude here, as the eccentricity increases, these factor NC, NQ and N gamma decreases even for the same value of phi. That means, here because Marov, what Marov have done? Marov have used the reduced width, but here width is not reduced, rather you decrease the value of NC, NQ and N gamma accordingly to your eccentricity. So, that is the concept here, and these charts can be used for the design purpose. And if you have some phi values or let us say some E by B value which is in between like 0.1 and 0.2, then naturally you need to use the interpolation. So, this is the way how the chart should be utilized. Now, continue with that. Now, what we have considered so far, we have considered the effect of eccentricity on NC, NQ and N gamma, but there may be a case where we need to consider the effect of shape factor, depth factor and inclination factor, because this equation which we have discussed is for stiff footing, right. This equation which we have discussed is for this stiff footing, and equation 3a. Now, the same equation will be modified for when you are considering different shape of the footings as here, and this equation looks similar to what has been given in IS code 6403. However, effect of water table is not considered here. So, we already discussed this equation, and as discussed earlier, S, D and I are nothing but shape factor, depth factor and inclination factor respectively. The shape factor with effect of eccentricity is denoted by delta. Okay. So, when we do not consider, normally S is represent the shape factor, but what these researchers Prakash and Saran have proposed to use delta instead of shape factor, and then they have given the equation for delta gamma. Delta gamma is given using equation 4a, where you could see that this shape factor is not only a function of B by L, that is aspect ratio of the foundation width divided by the length, but it also depends on the value of E by B. So, when you change the value of E by B, then delta gamma will change, and if E by B equal to 0, then this equation will give you the effect of B by L only, that means the effect of shape only without eccentricity. Then the second factor for delta Q is considered 1 for all shapes of footing, that means irrespective of shape of the footing, delta Q is assumed 1, that means there is no effect of this factor. However, third one for cohesion term, delta C, which is the safe factor for NC term, they have delta C equal to 1.2 for square footing and delta C equal to 1 for strip footing. So, strip footing means when the length of the footing is very large compared to width, or let us say when L by B is greater than 8, then assume this delta C 1. If it is L by B equal to 1, that means square footing, then assume 1.2, but there may be case when L by B between 1 and 8, then naturally you need to use the interpolation, and the value of delta C will be somewhere between 1.2 to 1. So, this is the case. So, this completes that how to go with for bearing capacity using the new method. But now let us see what happens to settlement when you consider the settlement. In case of this new method, the researchers have proposed also to the settlement, and when you have centrally loaded footings, means if there is no eccentricity, in that case settlement can be found either using plate load test, or you can have a the methods of settlement load test given in code IS 1888 1982. So, that can be simply used. However, that method cannot be used when the footing is subjected to eccentric loads, and so here a design method for determining the settlement and tilt of an eccentrically loaded footing for a standard load test has been proposed. What has been we are going to discuss? There is an eccentrically loaded footing settles as shown in this figure. So, let me discuss this figure first and then we will come back this one. So, what you have in this figure, I think this is quite clear visible to you. The top dotted line is the initial position of footing, that means without applying any load. Okay. Then you apply some a concentric load, that means some load if that is acting at the center, assuming q which is right now acting as some eccentricity, if I apply this load q at the center, then the footing will be displaced and this line will be there. So, this position will be the position when the footing is subjected to load at the center. However, what will happen that when the footing is subjected to eccentric load, then like you can say like this, and eccentric, if load is acting at the center, whole of the footing will come down, you know that in one level. However, if your load is acting more on one side, then what will happen that you have that one part of the footing will settle more, another will settle less, rather it will be tilted. So, which could be seen here. So, what happens? It is expected when it is subjected to eccentric load, towards the load side more settlement. So, it is more settlement here, and then the maximum settlement is at the A's. So, now we have 3 quantities S naught, SE and SM. All 3 quantities, S naught is the initial settlement of the footing due to the concentric load, while SE is a settlement under Q when it is subjected to eccentric load, SM is the age of the footing when it is subjected to eccentric load. Using this figure, we can easily derive equation 5, where SM is nothing but SE plus B by 2 minus E multiplied by T sin T. This is the T actually, this is not T naught, this is T only. So, what do you have? Here there is a small assumption. What is assumption? It is assumed that the T, angle T is a very small. As a result, this distance B by 2 minus E, though this distance is from here to here, that means there is a, if for a small angle, diagonal as well as base will be the same. So, that means sin T and tan T will be the same when the value of B by 2 minus E is small. So, for this small value of B by 2 minus E, we can have this equation 5. Naturally, this equation, here there are 3 quantities, one is your SM, SE and T. Out of these 3 quantities, SM, SE and T, if you know any of these 2, then you can determine the value of tilt. For example, if the value of maximum permissible settlement SM is given to you, the allowable tilt is given to you, then you can calculate the value of SE from this equation. So, like for a given eccentricity. So, this is the case. Now, continue with this, and so what the authors Prakash and Saran have done, they have measured from the test the value of SE and T from the field test, and then SM was computed using equation 5. Once SM is computed, then the settlement S naught of such footing under the central vertical loads were also determined. So, they know the value of S naught as well as SM and SE was also calculated. So, finally, doing these tests, because from the test results they know the value of SM, they know the value of SE, they know the value of S naught for different values of eccentricity, and finally, they have come with the empirical relation which denotes this ratio SE by S naught and SM by S naught in equation 6a and 6b. See, in equation 6 and 6b, these are functions of E by B. So, you have SE by S naught 1 minus 1.63 E by B minus 2.63 E by B whole square plus 5.83 E by B cube. So, what you have, that means this is functions of, so both the equations I can simply say that these are functions of E by B, or the values are functions of E by B, or this f can be written like this. So, what you have now, one thing is there that these equations 6a and 6b are applicable for E by B less than 0.4, because these equations are derived from the test where the value of E by is kept, maximum value is kept up to 0.4 only. So, these equations are based on the field test which is conducted on the footings, and then they have been converted into empirical relations. So, while using these equations we need to have the value of E by B less than 0.4, but normally the value of E by B is normally very less compared to 0.4, it should be less than 0.16 or at the most 0.2 to avoid the this loss of contact of footing. So, this will not be a big issue for this. So, continue with this settlement what we have, and when you have the settlement of the footing which we called S naught in this method is nothing but that is SF which we have used for the settlement of the footing, and this is calculated using the plate load test. Plate load test we have already discussed, and as we discussed earlier, for the sand you have a relation between the settlement of the footing divided by the settlement of plate, this is the ratio, and then here also you have on another side. In these equations, particularly in equation 7a, as we discussed that both BF and BP should be in centimeter or in centimeter, because 30 is coming. So, when you use this equation, make sure that this BP and BF are kept in centimeter, and then you will find the ratio here, the same thing is here. For clay, this is the equation, but this equation does not carry any 30 or like this. So, it is no problem even if you keep in meter or millimeter. So, that is not the case. Both of these equations 7a and 7b we have already discussed. Now, what you have from these equations, let us say you have the data of plate load test. If you know the plate load test data, then you can get the value of using the plate load test data, you can find the value of SF. Once SF is known, your S naught is nothing but S same as SF, and once S naught is known, then we can get the value of S and SM using equation 6a and 6b, and finally using equation 5 you can find the value of tilt T. So, once T is known, then make sure that this value of T is less than the permissible value of tilt, and once it is less than, then you are fine with that your design. So, this completes on the bearing capacity and settlement. These methods was coming from these two references so far whatever we have discussed. One is from Samshed Prakash's book on soil dynamics, another is from Swami Saran's book of 2006 on soil dynamics and machine foundation. Actually, what we have discussed in this lecture today is a new method for eccentrically loaded footings, how to calculate their bearing capacity and settlement. Now, in the next lecture what we are going to discuss that how to implement this new method for a design of footing. So, we will talk about in the next lecture design procedure, as well as we are going to discuss a design example. With this, I thank you very much for your kind attention, and let us meet for the next lecture. Thank you.